Well, okay, maybe we can get started. Good afternoon, everybody. It's a pleasure to introduce to you today our colloquium speaker, Takashi Moriya from the National Astronomical Observatory of Japan. So I've known Takashi for a while. The last time I saw him, we were in Japan for a workshop, and this was at the end of February last year. So it was right at the start of the pandemic. And while I was there, Japan was starting to shut down, the schools closed. So it was a very strange conference. And of course, a couple of weeks later, everything shut down in the US. And of course, we've been in the pandemic ever since. But the silver lining of this is that we get to invite great scientists from all over the world to give our colloquia. And so we're very lucky today to have Takashi joining us from Japan. And Takashi has done some very impressive work over the last several years. I counted you've published somewhere between 20 and 30 papers over the last 5 years. So a lot of impressive work, largely focused on supernovae and transients. And today, Takashi will be telling us about massive star mass loss from supernovae. So Takashi, the screen is yours.
Thank you very much for the introduction. So thank you very much for inviting me to give a colloquium here. Of course, it's better to be in California, but yeah, it's good to be able to give you this talk from Japan now. Anyway, I'm going to talk about supernovae, but especially focusing on mass loss of their progenitors and what supernovae will tell us about the mass loss, especially from massive stars. So I think you know this, but just in case to start, supernovae explosion of stars, and this is one of the most famous example, 9087A, and yeah, this star there exploded as supernovae. And in this talk, I will focus on massive star explosion or core-collapse supernovae, and their explosion of massive stars about 8 solar masses. This is HL diagram, and theoretically we expect red supergiants sitting here, and also Wolf-Rayet stars sitting around here as supernova progenitors. We also know some luminous pool variables explode. But in this talk, I will focus on red supergiants because of the limited time. And I will talk about what supernovae will tell us about the mass loss of red supergiants. And red supergiants are actually observationally confirmed to be progenitors of supernovae. So sometimes when supernova occurs, they happen to have some images before the explosion. So we can check what kind of star was sitting at the location of the supernova. And then, of course, we can observe again back after the supernova is gone, and then we can confirm this red star here actually disappeared. So this was actually the progenitor of this supernova. We now have dozens of cases of such confirmed disappeared red supergiants, and we can plot the property of these disappeared stars in HL diagram and compare with theoretical star evolution tracks. And these black dots are basically those stars which were confirmed to be progenitor of supernovae, and which were red supergiants. And well, these upper triangles, the upper limits they got. And based on these direct observation of red supergiant. Observationally, we know roughly red supergiants in the luminosity range of 4.4 to 5.2 in this unit we explored as supernovae, and these are corresponding to roughly the zero-age main sequence mass of 8 to 20-ish solar masses. And when these red supergiants explode, they are observed as type 2 supernovae. And if you are not familiar with this supernova classification, you don't need to care about them. Type 2 basically means there are hydrogen signatures in the spectra. And of course, red supergiants has extended massive hydrogen-rich envelopes. So that's why we see hydrogen in the supernovae from them. And these type 2 supernovae are characterized by like plateau, so-called plateau phase lasting for 100 days, during which the luminosity doesn't change much and then keep declining. And these type 2 supernovae actually, most of the core-clef supernovae are exploding as type 2 supernovae. And in this study, they found like 70% of core-clef supernovae should be, it's observationally found to be type 2 supernovae, which means explosion of red supergiants. And based on this light curve and spectral property, we can also estimate the ejecta mass and explosion energy from supernova properties. And these are estimated properties of red supergiant explosions. So each dot shows one type 2 supernova. This circle basically means the uncertainty. But anyway, we typically have, let's say, 10 solar mass-ish ejecta with 10 to the 51 L explosion from these red supergiants. And as I said, I would like to focus on the mass loss of these massive stars. And mass loss is a very important factor determining the fate of massive stars. And of course, in the current era of gravitational wave astronomy, this is getting more important because this mass loss determines the final remnant mass of this massive star evolution. This is one example showing the importance of the mass loss in determining the black hole masses in this case. So this is the age main sequence mass, and this axis is the black hole mass resulting from this initial mass. And with the standard mass loss rate, you expect this, relatively low black hole mass, but just by changing this mass loss rate by factor of 2, then you get the remnant mass of very different mass from this standard value. So this, to determine, to understand what the progenitor of these gravitational wave sources, this understanding of massive star mass loss is quite essential. And in this talk, I will focus on red supergiants. Red supergiant, the mass loss from red supergiants, especially. This red supergiant mass loss rate is known to be very uncertain, not well determined. So, and here I show several prescriptions used in stellar evolution theory as a function of luminosity. So this is red supergiant luminosity and mass loss rate. And as I said, just factor of 2 will make quite different prediction, where, in the final fate of massive stars. But this uncertainty in mass loss prediction has like more than factor of 10. It's determining these, which prescription better explains the red supergiant mass loss rate is very important. And but red supergiant phase is just located in the final million years of the stellar evolution before the explosion. So it's quite short time compared to the entire life of a massive star, which lasts tens of millions of years. But actually, this mass loss during the red supergiant phase is quite important, as you see in this figure. So this is years to the explosion. So it's the star explodes here, and this is an example of 16 solar mass stellar evolution. And during the main sequence, it's because you have more than 10 million years of time during the main sequence, but the mass loss rate is not that high. And the red supergiant phase, the lifetime is 10 times shorter, but the mass loss rate is actually more than, in this particular case, factor of 100 higher than the mass loss rate during the main sequence. So actually this mass loss during the red supergiant phase is determining the final mass and the final fate of these massive stars. So what I want to say is this understanding of red supergiant mass loss is extremely important in understanding the massive star evolution. So these supernovae from red supergiants, when they explode, of course, they explode after this mass loss happens. So that means these supernovae occur in the circumstellar matter formed through their progenitors. So this is one example of the simulated circumstellar structure of the red supergiant explosion. So of course, the material lost during the main sequence goes further away, and just on top of the supernova progenitor, there will be the wind formed through its supergiant phase. So basically, when the supernova from red supergiant explodes, this supernova ejecta hits the circumstellar matter formed during the red supergiant phase, and which means that if we can find some circumstellar matter signatures in type 2 supernovae, then we can get information on red supergiant mass loss through type 2 supernovae. So this is kind of schematic picture of what's happening after the explosion of the supernova in the red circumstellar matter, and the supernova ejector will hit the circumstellar matter, and then between the circumstellar matter and supernova ejector, there exists a blast wave or forward shock running into the circumstellar matter, and then of course there will be contact discontinuity, and this is shocked circumstellar matter, and then there will be shocked ejector, and then reverse shock going into the supernova ejector exists. So what directly interact with the circumstellar matter is this forward shock, and actually this forward shock will emit the synchrotron emission that can be observed in radio. So basically, this forward shock will accelerate electrons, and then we can observe this synchrotron emission from these accelerated electrons. And so that will basically give us the kind of direct information about the circumstellar matter density and from which we can estimate the circumstellar matter density, and which can be can be interpreted in terms of mass loss history of the progenitor. And typically, radial light curve from supernovae has a single peak light curve. Actually, it's not that simple usually, and we have some wiggles and so on. But usually, broadly, we can interpret in the single peaked light curve. This peak luminosity and the time of the peak is basically determined by the absorption processes happening at this synchrotron emission. And when the circumstellar matter density is relatively low, synchrotron self-absorption is determining this peak. And when the circumstellar matter density is relatively high, then we need to think of free absorption at unshocked circumstellar matter. Anyway, in either case, from this rise time and from peak luminosity of radial light curve, we can estimate the circumstellar matter density and the mass loss rate of these supernova progenitors. What was very nice in recently, of course, there has been many radio observations, but there was, many were mostly actually they were upper limits non-detections, which just sent to ATELs and so on, not much published. But recently, this work compiled all the detections and the upper limits publicly available, and estimate the distribution of the rise time and the peak luminosity of supernova in radio. And this is a summary of this work. And basically, this rise time and peak luminosity will be in radio will be distributed there. And we focus on type 2s, so they have this distribution. And the question we want to ask here is if this peak luminosity and rise time, if we can constrain the uncertain red supergiant mass loss prescriptions we saw previously, which had uncertainty of more than factor of 10, if we can constrain them based on these observations. So if we we can write down some equations for the synchrotron emission, and assuming some supernova properties, we can theoretically write down these radial light curves. And as I said, these characterized by the one single peak. And this I show here the example of the radial light curve in one mass loss rate, 10 to the minus 6 solar mass per year. And then, of course, for a single mass loss rate, we expect to have the supernova properties can be quite different. So we changed the ejecta mass from 5 to 20 and the explosion energy of 10 to the 50 Ls to 2 times 10 to the 51 Ls, which is in the range of type 2 supernovae. And if we write the radial light curve for all the combination of these possible ejecta mass, then we have this line for the radial luminosity peak. So for a given mass loss rate, we expect this peak luminosity, peak of the light curve is expected to be in this one single line. And of course, we can write this line for different mass loss rates. And then we take, for simplicity, I showed this, many red supergiant mass loss prescriptions, but broadly speaking, it can be classified into relatively low ones, relatively high ones. So we take this low de Jager type mass loss rate, and also Van Loon like mass loss rate, which is relatively high. And the supernova luminosity, red supergiant luminosity range of supernova progenitors, as I introduced before, from luminosity is about 4.4 to 5.2-ish. So this is the red supergiant progenitor luminosity range. So this is the range we can investigate through supernova red supergiant explosions. And there's some argument the red supergiant in this higher luminosity range may also explode as supernovae, which we don't know. So anyway, I will show this range in the gray in the following figure. So this is what we expect from this de Jager type mass loss prescription and the Van Loon like mass loss prescriptions. So again, this is rise time and this is peak luminosity. And this blue circle means the observationally expected region for the radial peak rise time and peak luminosity. And this each red dot is the observed peak luminosity and rise time. And of course, this blue line is drawn with, combined with many upper limits. So actually, we expect to have many smaller luminosity regions. So observations observations are kind of biased towards the brighter end. But anyway, this is for reference. I'm showing these red dots as well. And as I introduced before, each line shows one mass loss rate, and which is function of luminosity. So this is this colored region is red supergiant supernova progenitor luminosity range, and the gray is uncertain. But anyway, this is what we get from these two mass loss prescriptions, and we can see that the de Jager type mass loss prescription is better explains this radial peak luminosity and the rise time relation for several reasons. One is that it covers large area in rise time and peak luminosity region. So you can see this Van Loon type prescription only covers very small range of rise time and peak luminosity. Especially rise time is very narrow in this Van Loon cases, while de Jager type mass loss prescription predict very wide range of rise time as observed in the actual radial light curve from type 2 supernovae. And this is basically because of the wide mass loss range, wider range of mass loss rate covered by de Jager type mass loss prescription. So if we see this luminosity range, this de Jager type mass loss prescription ranges from about minus 6.5 to like minus 5-ish. So quite the dependence on the luminosity is relatively large and covering the wider mass loss rate in the supernova luminosity range. So that can explain the widely spread luminosity in rise time and luminosity observed in radio light curve, while the Fandun mass loss rate they don't have much dependence on luminosity, so they expect to have very small mass loss variation in the red supergiant supernova progenitor, which is actually not consistent with this large region covered by radio rise time and peak luminosity. And also, Fandun type mass loss rates predict, only relatively large range of luminosity. This is again because of the high mass loss rate of the Fandun-like mass loss prescription. They don't have much low mass loss rate supernova progenitor, so they cannot cover this lower mass region. And of course, this is just, I'm taking the mass loss rate from this line, and actually, mass loss rate can vary from stars to stars. So we can, we checked within a factor of 10 what happens, and also in this figure, I only considered synchrotron self-absorption, but when the circumstellar density is high, then free absorption should play a role, and that will make the rise time larger than what's expected from free synchrotron self-absorption. So basically, this includes everything, and as you can see, the Jaga rate covers relatively good, explains this wide expected range, observed range of radio rise time and peak luminosity, while Fandun rate is still suffering from the explaining this variety observed in the radio supernova light curve. So from the radio observations, we can say that this Jaga type mass loss prescriptions covering from relatively low mass loss rate to relatively high mass loss rate in the supernova luminosity range is preferred to explain the radio properties of type 2 supernovae. So far, I have discussed the radio properties of the supernovae, and which is, this rise time is, let's say, typically more than 10 days. So that means what we have investigated so far is we use the information after 10 days after more than 10 days after the explosion. And if we set supernova shock velocity of 10,000 kilometers per second, then in 10 days this forward shock will travel like 10 to 15 centimeter roughly. So if we use the information of supernovae after 10 days after the explosion, then which means we are probing the circumstellar matter above 10 to 15 centimeter. And then the typical red supergiant wind velocity is about 10 kilometers per second. And so, which means, to reach the circumstellar, for the wind to reach 10 to 15 centimeter, it takes about 30 years. So if we are looking at the circumstellar matter above 10 to 15 centimeter, that means we are, tracing or investigating the red supergiant mass loss history more than 30 years before the explosion. So what we learned so far is that red supergiant mass loss rate more than 30 years before the explosion can be well explained by the Jaga type mass loss prescription. But what about within 30 years before the explosion? So of course, we may think nothing will happen within 30 years before the explosion, but actually we start to see that's not the case, and I will introduce that here. So type 2 supernovae, it has been many good observations recently, and there are several good observations more than 10 years ago, and of course theoretical model has been made, and this is one example of classical type 2 supernovae 1990 EM, which was very well observed supernova back then, and there was a theoretical light curve model which explains good this plateau phase in multicolor very well. But if we look carefully, actually, this early phase is, not well modeled since from back, as you can see from here. Back then, we didn't care much about these early phases. But as we start to get a good observation of type 2 supernovae from early on, we start to recognize this is actually a serious issue. And again, this is a zoom up of this theoretical light curve from red supergiant, and actually observed type 2 supernova light curve from early on. So theoretically, we expect the optical light curve to rise in, let's say, especially in the optical light curve to have the rise time of more than, let's say, 10 days or so. But from about 6 years ago, we started to realize that actually type 2 supernovae, systematically have much quicker rise time than we expect from the theoretical light curve. And so the question back then was why there's this big discrepancy. And a big hint to answer this question was provided by this great IPTF supernova, 2013 FS. And this supernova was discovered by PTF like within 3 hours after the explosion, which is amazing. And what was also surprising was just after the discovery, some people sitting at the cake and they could observe this supernova, and the first spectrum of this supernova was taken at 6 hours after the explosion. So these spectra they took, and this is the 6 hours after the explosion, 7, 9, 10. What was amazing is we saw this very narrow line at the beginning, which disappeared as time goes, and then after a while it became a normal type 2p supernova spectra. So there's nothing. If we were observing this object like from 10 days after the explosion, there was nothing special about this object. But this early spectra was, very different from what we typically see from type 2 supernovae. And then this early spectra was modeled, and especially, this emission line actually indicates there should be some dense material must be there. Based on the spectral modeling, one can estimate the circumstellar density around this type 2 supernova progenitor. And this is what they got. So this is the radius from the progenitor, and this is the density. Based on the spectral modeling and this early spectra, they found that the circumstellar matter density should be somewhere there. And as we introduced before, the observation based on radio observation of type 2 supernovae, which basically constrain the mass loss rate above 10 to the 15 centimeter, indicate they should typically have mass loss rate of 10 to the minus 5, 10 to the minus 6-ish mass loss rate. So the expected, if we draw a line of this mass loss rate, the expected density from this mass loss rate, then we expect to have the density of around here, which is quite different from what they find here. So as shown in this plot, somehow above the 10 to the 15 centimeter, the mass loss rate is basically, they also have radio observation for this object, so it's consistent with the standard, the mass loss we discussed so far. But within 10 to the 15 centimeter, somehow this circumstellar matter density is getting extremely high, and in this particular case, and this is something is actually seems to be happening within decades before the explosion. So that was a big hint. And while we focused here is that if we have such high density in around just above the supernova progenitor, then there will be supernova ejecta hitting this dense circumstellar matter. Then there will be strong shock wave formed in between the ejecta and circumstellar matter, which can efficiently convert the the kinetic energy of this supernova ejecta to radiation. So if the circumstellar matter density is low, then we only see synchrotron emission, which there's not much effect on the optical light curve. But the dense, if the circumstellar matter is extremely dense, like we see in the case of this object, then we also should have some effect on the optical light curve. So we saw the effect of the this dense circumstellar matter in the spectra so far, but we investigate what will happen to this optical light curve if there's such a dense circumstellar matter is existing just above the red supergiant progenitors. So yeah, this is just details. We these radiation hydrodynamic dynamic simulations using stellar code. So this luminosity will be affected by this this shock, which is basically this kinetic energy of the supernova ejecta is converted to radiation. So we need to deal with the radiation hydrodynamics. This code also allows us to model the multi-group, multi-frequency light curve, so we can get light curve in different bands. And we took several red supergiant progenitors and put dense circumstellar matter up to 10 to 15 centimeter, as I introduced. And this early type, and then we put thermal energy to let the star explode. We put some nickel, but we focus on the early phase light curve, so this nickel is not relevant here. Anyway, we put this kind of structure, and actually, so this is just above the progenitor. So within 10 to 15 centimeter, if we just put the constant wind, then we get this line. This is the case of 10 to the minus 4 solar mass per year. But yeah, there will be a huge jump in between. And of course, at the surface of the red supergiant, the wind velocity is should be close to 0, and then gradually wind should be accelerated. So we took several formula for the wind acceleration. This is also kind of uncertainty related to the uncertain mass loss mechanism of red supergiant. But yeah, we took several possible density structures there and put this kind of structure on top of the red supergiant progenitor, and then let it explode and see what happens to the light curve.
Takashi, you've got about 10 minutes left.
Yeah, thank you. So this is the bolometric light curve. So this black line is basically what you expect from the without circumstellar matter. And as we have, they put the higher density, higher mass loss rate, then we have more effect on the bolometric light curve because of this interaction. We have more, as the density gets higher, the luminosity gets higher from this interaction. And then this is the optical light curve. And as we saw, so this is the circumstellar matter, the model without circumstellar matter. And as we put this dense circumstellar matter, then we can see, this rise time in the optical light curve is getting faster because of this early interaction providing extra light in the supernova light curve. And this is the effect of the in G band and R band, and this is optical rise time and the optical peak magnitude. This open circle basically shows the model without circumstellar matter, and here I show many combination of parameters dependence on the mass loss rate and this wind structure and the explosion energy. Smaller symbols have smaller explosion energy, but in any case, you can see as the density gets higher, then the rise time gets shorter, and that can actually explain this difference between the original theoretical light curve, which basically didn't have circumstellar matter. But if we put like about 10 to the minus 3 solar mass per year circumstellar matter, then we can explain this very quick rise in the optical light curve. So we found in this particular case where we had this quick early spectral observation, from the spectra we found there should be dense circumstellar matter just above the supernova progenitor. Then actually that is also consistent with this quick rise observed in the optical light curve, and this mass loss rate is consistent with what was expected from the early spectral modeling. And this so far I showed in the case of this particular supernova, but of course the next question is how general this how a mass loss enhancement is observed in these red supergiant explosions. To investigate this generality, we collaborated with these people in University of Chile, and they actually performed high cadence transient survey using the DECAM. Their purpose was to observe the shock breakouts from supernovae, and they found 26 type 2 supernovae just after the explosion. And this is all the 26 type 2 supernovae with early detection in G band, which is shown in green, and R band, which is in red. And as in this figure, dotted line is the model without circumstellar matter, and the solid line is the model with circumstellar matter. And in this case, we did MCMC fitting to estimate the parameter range to explain this early light curve. And so out of 24 supernovae, type 2 supernovae, out of this 26 supernovae actually required this dense circumstellar matter to explain this quick rise observed in type 2 supernovae. So there were only like 2 exceptions, which we didn't require this dense material just above the supernova progenitor. And otherwise, it was the light curve was too quick to explain this rise time without circumstellar matter. And we also fitted the old well observed supernovae as well, and this is what we found. And so this is mass loss rate we estimated based on this early rise time, which means the mass loss rate within 30 years before the explosion. And this is the density structure, which doesn't matter, actually, not well constrained. But anyway, mass loss rate should be order of 10 to the minus 3 solar mass per year, as we found in the case of 2013 FS. So actually, this mass loss enhancement happening within decades before the explosion in red supergiants seems happening very commonly, or in most cases, this is observed. And this is the distribution we got from mass loss rate distribution. And yeah, of course, observational bias is there, so we corrected for that. And black line is the final distribution we estimated. So to summarize what I have talked so far, which basically I was trying to constrain red supergiant mass loss history based on the supernova observation. And in the earlier part of my talk, through the radio observations, we learned that the mass loss prescription of degenerate type is explaining the radio property of supernovae from red supergiant very well. So red supergiant mass loss rate should be following like 10 to the minus 6.5-ish to 10 to the 5-ish. So this is based on the information above 10 to the 15 centimeter, which basically means mass loss before the 30 years before the explosion. But then, based on the optical light curve, optical rise time of the red supergiant explosions, then to explain quick rise time, we need 10 to the minus 3-ish solar mass per year within 30 years before the explosion. So what we found is that there should be mass loss enhancement in the final decades before the explosion. So this was what I showed at the beginning, but actually in the final decades towards the explosion, this mass loss rate seems to be somehow shooting up. That's what we start to see from the supernova observation from red supergiants. And this is kind of, the question is why this is happening within 30 years before the explosion. So there's many ideas, like Jim is investigating, like gravitational wave-driven mass loss. And what's, of course, what is mystery is the explosion of star is triggered at the center of the star, with the mass loss is happening at the surface of the supernova progenitor, and we didn't thought mass loss would change within 30 years before the explosion, because this is too far to affect each other in 30 years. So we thought this timing core collapse shouldn't be much related to the surface mass loss, but actually now there are many evidences that there seems to be this somehow this core collapse is triggering the mass loss at the surface of the explosion, and this exact mechanism is we don't know exactly yet, and that needs to be investigated more. And finally, next question is, I have talked about the red supergiant explosion so far, but of course, remaining 30% has of the core of supernovae doesn't have much hydrogen, and what's happening there? So they are stripped envelope supernovae are coming from Wolf-Rayet stars. The question is, do Wolf-Rayet stars have similar kind of mass loss just before the explosion, and similar mechanism to red supergiants inactive there? That's next question we need to ask, and that would be interesting, I think. And we start to see some examples of this kind of mass loss enhancement happening just before the explosion in Wolf-Rayet star explosions as well. This is one example from U again. This is prototype type 1c supernovae, but we had some signature even before. And in the case of the, in the relation with gravitational wave astronomy, this is very interesting. And I don't have much time, but the ultra-stripped supernovae are suggested to be a progenitor of double neutron stars, which leads to the neutron star merger. So this is, but to make a close neutron star binary for the gravitational wave sources, the star needs to go through special supernova, which is called ultra-stripped supernovae. And actually nicely found this ultra-stripped supernovae a few years ago. And this supernovae had very, we had some prediction for ultra-stripped supernova properties. And this supernovae matched very well to that observed, theoretical prediction. But we didn't predict there should be some, circumstellar matter. So this early phase, so this theoretical light curve we predicted before was just this rising part. But what Sherry found is that there is this early phase, very luminous phase, during which there was a circumstellar matter interaction observed there. So we thought, there's after some mass transfer in this binary system, this will just explode. But there seems to be, just after this mass transfer, there's not much time left to explode. But just before the explosion, like as I said, in a similar time scale to red supergiant, like within 10 years before the several decades before the explosion, these stripped envelope stars leading to ultra-stripped supernovae also seems to have this intense mass loss just before the explosion. So this is Wolf-Rayet star, which is not red supergiant, but this kind of star is also experiencing some mass loss just before the explosion for unknown reason. We are starting to see this in the ultra-stripped supernovae. And there, I took this from his PhD thesis, and we have now several ultra-stripped supernovae identified so far, leading to several different compact binaries. But I believe in most cases, we see this signature of late phase mass loss enhancement happening, just before the explosion. So in the case of this ultra-stripped supernovae, we clearly seeing some mass loss enhancement happening. And that's that's very interesting to investigate more. And as I said, some stripped envelope supernovae, we start to see this kind of mass loss enhancement happening just before the explosion. But of course, we want to check if normal or canonical type 1bc supernovae really have this kind of mass loss often or not. And we need to investigate what's the mass loss signatures as well. Yeah, I'm running out of time, so I will just show the summary. But yeah, I hope I convinced you the supernova is a great tool to investigate the massive star mass loss as well. That's it. Thank you very much.
Okay, thank you, Takashi. All right, we have time for a few questions, I think. So please raise your hand with the raise your hand tool. Okay, we have a question from Wenbin.
Hi, very nice talk. So how do we know about the asphericity? How to say about the CSM?
Yes. So here, what I talked is I assume totally spherically symmetric circumstellar matter, and but the circumstellar matter can be clumpy, and of course can be asymmetry as well, as you said, and this can be investigated through like the shape of the spectra if we can take them, and from the light curve point of view, it can be also the viewing angle dependent, and actually we started to investigate this viewing angle effect as well. And there's actually quite a viewing angle dependence, but there, and that's really depends on the disk shape and covering factor and so on. That's something complicated that we need to investigate more.
Thanks.
Okay, next a question from Shri.
Yeah, so if you have a very dense shell, ejected before the star dies, and you have this additional interaction, which you explain as giving rise to this optical light, there should still be radio emission from that. Now it will be absorbed, at the usual low frequencies. Yes. But I did a very quick computation. It's it is detectable with ALMA.
Yes.
So that might be worth.
Yes, actually, we Keiichi Maeda at Kyoto University is leading this ALMA proposal to find, quite early emission from the supernovae. And as you said, to invest, so synchrotron, the absorption will be, you can have, for that frequency, you can have earlier information because they are transparent early on. So this ALMA will be really good to have this very inner circumstellar matter information. And we actually detected some supernovae with ALMA, and that result should be open soon.
Okay. The other comment I had a question, which is your HIT survey. Mm-hmm. Did you get any redshifts for those objects? Because in the absence of that, I think interpreting would be difficult.
Yes, so we have spectra for 1/3 or half of them actually, and remaining doesn't have spectral information. So half of them have with spectral information, and we did type classification based on the light curve fitting actually. Then so we did light supernova classification based on the light curve, and then afterwards we checked those with spectra, and all the supernova we classified as type 2 had a type 2 spectra. So of course half of them is not, we don't have spectral classification and we don't have redshift, but we succeeded. Our classifier was good to classify those with spectral information. So we thought our classification scheme is good, and we put every supernova we classified as type 2 based on our light curve fitting as a type 2s. So yes. So the short question is, we only have information for redshift of half for half of the type 2s.
Yeah. So I have My slight concern with this kind of a statistical approach would be when you say something is type 2 and you're classifying, okay, what does it mean actually? It means that you expect to see a plateau, a decline, and an exponential decay, something of that sort. But
Yeah.
there's no reason to believe that the plateau value is constrained at all. I mean, can I invent a new some explosion which looks that way, has a plateau and a decline, and is arbitrarily bright?
Yes. So in that sense, it's, we did this kind of study several years ago, but now all ZTF samples is there, and we have much more type 2s, I guess. It would be great to do this kind of study again with, well known sample with good redshift estimate and so on, and see if this conclusion still holds or not.
Well, the main reason I'm still sticking at this is that I've noticed that with these DECAM surveys, which are highly sensitive but narrow band, that they naturally pick the brightest events.
Yes.
So I think there's a tremendous Marquis bias where there's this sort of a statistical approach or flux limited approach will, I think, give you a view of these exploding stars at the very brightest end. I think most of them are pathological, actually. So I think the right way to do this for the mass loss thing is you got to define a volume limit, or you have to have,
I agree,
or you have
yes.
to work at a sensitivity level that is very high, so that the fact you're not just finding it the the weirdest objects which happen to be the brightest.
I agree. We tried to correct for this, but back then, but of course, as I said, it's best to limit our samples in the volume limited sample, and yeah, we didn't have that stuff back then, but I guess now you have those. We should do this again with your ZTF sample, I think.
Okay, thank you. I think if we want to discuss this further, we can do it in the faculty meet and greet, but I think we should let everybody go. So let's all thank Takashi one more time. Thank you, Takashi.
Thank you.
Faculty, please stick around. Monsi, I'm sorry I didn't get to you. I know you have a question. Hopefully you can stick around.